Hello everyone, my name is Wei. I'm a fourth-year PhD student from Robotics Institute, Carnegie Mellon University. Today I'm going to introduce our recent work called Provably Safe Tolerance Estimation for Robot Arms via Sum of Squares Programming. This is the outline of today's talk. Now let's start with the motivation of our problem. Let's start with our presentation with a motivation problem that arises during the actual control phase for trajectory following. Here is a real-world intelligent robot polishing task, where the robot is supposed to do automatically polishing of the weld bead inside of a workpiece. Now let's see this video. Here we plan a collision-free trajectory. The robot will remove weld bead inside of a workpiece. As you have already noticed, since we're actually conducting the weld bead removal, well, the robot effector will maintain contact with the surface, and the bumpy inner surface will cause some perturbance for the tracking controller, which will further cause the track robot configuration deviate from the planned configuration, and the potential collision will happen. We desire to design a robotic controller to make sure the robot can smartly adjust the wrist joints to ensure the robot can still maintain contact with the surface while guarantee the robot will be free. However, it is impossible to design a safe controller without the knowledge of what is the maximum allowable deviation tolerance with respect to the reference plane configuration. Now let's see a more simple case as illustrated in this figure. Suppose due to some disturbance, some deviation from the reference pose happens during the control tracking phase. And here we just use two-link arm robot as example. Let's say the reference pose of the robot is the solid gray pose, whereas the robot may end out as the light gray pose during the actual control. Although disturbance and tracking error is inevitable in real-world application, we want to synthesize a safe controller to ensure that the deviation can be bounded, and any deviation pose inside of the bound is guaranteed to be safe. And therefore, we want to estimate the maximum allowable deviation bound, such that any controlled deviation within the joint tolerance estimation bound is guaranteed to be safe. Here is a very good illustration of the joint tolerance bound. Let's view the joint tolerance from the robot configuration space perspective, and where there are two variables. One is the first joint angle, and the other is second joint angle. Therefore, reference pose is a point in the configuration space, and the actual controller pose is another point in the configuration space. Due to the presence of the obstacle, there is an invisible set in the configuration space. And what we desire is to find the safety joint tolerance estimation bound hypercube with respect to the reference pose, such that any deviation inside of the hypercube is guaranteed to be safe. Now, for the joint tolerance estimation problem, recall that the mathematical problem for joint tolerance estimation is this equation. Now we desire to find the maximum tolerance lambda, such that every point inside of the infinite norm ball will satisfy the constraints. Therefore, every x corresponds to a constraint, and there are infinitely many x inside of the infinite norm ball that satisfies. And we can easily see that it essentially contains infinitely many constraints during the optimization of lambda. Thus, the challenge is how can we solve an optimization problem with infinite number of constraints. Now we're ready to present the problem formulation. Since we're to solve the problem optimization with infinite number of constraints, mathematically, given feasible reference state XR, we want to find a bound lambda such that any deviation within the bound, the robot is safe. This is called tolerance estimation problem. And here we focus on infinite norm case, where infinite norm ball is equivalent to a hypercube in the configuration space. Here we provide an example on 2D link planar robot arm shown below. The problem is to find the maximum allowable deviation from reference pose such that the end effector of the robot does not hit the wall. Suppose the length of the two links are both 1 and xi is the ice joint angle for the robot involved frame, then the collision avoidance constraint can be written as this. The tolerance is illustrated as the green square in the configuration space. Before we introduce the proposed X solution, we would like to first discuss the existing works to solve the similar problems. Now, regarding the related works for solving the joint tolerance estimation problem, there's very limited research works to solve this problem in the context of the robot arm. However, there are some generic methods to solve the regular problem form. One category of the methods is the reachability-based methods. Reachability-based methods solve the problem by proposing different lambda, computing the reachable set, and then performing binary search to find the maximum lambda such that all points in the reachable set R satisfy the constraint fx is greater or equal to 0. However, exact reachable sets are expensive to compute, resulting the solution is either unsafe or too conservative. Besides the reachability-based method, adversarial optimization can also solve an equivalent form of our original problem, which finds the smallest possible deviation such that the constraint is about to be violated. Numerically, this equivalent form is easy to solve since it can be directly fit into the existing optimization solver. However, due to the local optimality introduced by the complexity of the constraint, it is challenging to find a lower bound for the adversarial problem. Note that the joint tolerance estimation is hard to solve due to the fact that it contains infinite number of constraints. Well, in fact, there is another category of methods can actually handle infinite number of constraints, which is called sum of squares programming. The problem form of the SOS programming is to find the parameterization of fx such that every state x will satisfy fx is greater or equal to 0. A good example is shown here. Let's say we want to find a parameterization of fx such that every x, fx is greater or equal to 1. Then fx can be written as x squared plus 1, which is shown in this figure. So far, you may be wondering if we can directly use sum of square programming to solve the joint tolerance estimation problem. Well, the answer is no. Here we highlight the inherent difference between SOSP problem and the joint tolerance estimation problem. So basically, joint tolerance estimation is considering the local positiveness constraints, which means it only requires fx to be positive in a bounded neighborhood of the reference state. In example here, fx is positive in the unit cube around x equal to 0. However, SOSP deals with a more restrictive constraint, which is called global positiveness constraint, such that every state x should have fx greater or equal to 0. Although SOSP cannot directly solve the local positiveness constraint, our method is actually built upon a theory behind SOSP, and this will be introduced later on. Now we are ready to present the proposed method for solving joint tolerance estimation problem. Next, let's introduce the methods to solve the joint tolerance estimation problem. First, let me give you the definition of SOS polynomial, which means the polynomial that is a summation of a set of polynomials squared. Next, I want to introduce a theory that our method relies on, which is also the core idea behind SOSP to deal with a global positiveness constraints. The idea is, no, let's not directly deal with the infinite number of constraints. That's too hard. Let's try to show there does not exist any solution such that the condition is violated, which is to construct a refuse set and show it is empty. When we keep the core intuition of SOP in mind, now let's tackle JTE problems step by step. Since we want to leverage SOSP to deal with infinite number of constraints, we first transform the JTE problem into the optimization with polynomial constraints. And here, let's use a two-link example introduced before as illustration. Let's also get rid of the infinite norm by introducing two auxiliary variable x, y, I. We reach the following equivalent local positiveness constraint. Well, this looks better, but the problem is still it is not polynomial because it contains cosine function. But that's okay. Let's use Taylor expansion to transform the cosine function or triangolic terms into a polynomial. So basically, we're using small angle approximation to transform the cosine function into polynomial. And therefore, we have the following infinite number of polynomial inequalities where f1, f2, and g are all polynomial inequalities. Notice that current problem becomes to find a tolerance bound such that all stated within the bound gx will be larger than 0. Whereas the original problem is that all stated within the bound is fx larger than 0. So therefore, it is necessary that we to ensure g is definitely the lower bound of function f. And this part is rigorously discussed in the paper. And for now, we will continue with function g. Now we have the pretty good form that is close to the sum of square programming. However, the optimization problem is still differs from the standard SOSP due to the fact that the set of inequalities f1, f2, and g contain the additional lambda parameter to be optimized, and therefore the standard SOSP solver cannot be directly applied to address this problem. And therefore, we dig into the theory behind SOSP and use it to solve the problem. And eventually, a theory called positive statistic can be transformed of a problem into SOSP format as shown below, which means we optimize lambda such that there exists a set of positive scalar pi to make p0 is a sum of square polynomial. To solve the sum of square programming, we can efficiently transform it into a semi-definite programming problem where we do a sum of square decomposition of p0 and to show that q star is positive semi-definite. And the good news here is that q star is PSD can be verified by showing the determinant of all its submetrics are not negative. And therefore, the SDP becomes a normal nonlinear programming problem. And so far, we can see that we transform the original infinite number of constraints into a set of normal nonlinear inequality constraints, which can be efficiently dealt with using the current nonlinear programming solver. Now we have introduced the GTE algorithm procedure, and we come to the most interesting part. We can provably prove that the solution from GTE is the lower bound of the optimal solution of the original problem. So mathematically, if we denote the optimal solution of the original problem as lambda naught, and the solution from GTE is lambda star, then lambda star is non-negative and it is smaller or equal to lambda naught. Now we're ready to present the proposed method for solving the joint tolerance estimation problem in practice. We designed two sets of experiments for joint tolerance estimation. In these experiments, the obstacle is taken as a half plane. Two sets of problems are included. One is undegrees of freedom robot working in the planar space, and the other is robot working in the Cartesian space. Safety constraint require the inner factor should not collide with the half plane. For each problem set, we randomly pick the reference robot configuration. The fundamental constraint fx becomes that we enforce the constraint on the robot inner factor, such that fkx will be less or equal to cx, where fkx denotes the x-coordinate of the inner factor, and cx is a real number. To evaluate the performance of the joint tolerance estimation problem, we use four metrics as listed here. Feasible means the optimization problem can return a tolerance bound estimation. A tolerance bound is valid if all possible states within the bound are safe. Tightness is to judge the optimality of an estimated tolerance bound. We first test our algorithm on a planar robot platform where we test the robot with different degrees of freedom, including 2, 6, 12, and 20 degrees of freedom. To verify our algorithm, we compare it with adversarial explanation, which solves the following equivalent problem, where we add a slack variable to compensate the numerical error during optimization procedure. The comparison among GTE and adversarial optimization is shown below, where we summarize the average valid solution completion time, timeliness, and the feasible solution variance. We found that GTE algorithm will take the shortest completion time to find a valid solution, which is generally 2 to 10 times faster than adversarial optimization. Meanwhile, GTE also achieves the highest percentage of valid solution across all experiments, which indicates that GTE is robust with respect to the random initialization. On the other hand, adversarial optimization can hardly find any valid solution as the robot degrees of freedom increases. The timeliness also demonstrates the great optimality of GTE algorithm. Besides planar robot, we also tested robot with 2, 3, and 6 degrees freedom in the computational space. And for each experiment, we have computed the joint tolerance, and we randomly sampled 10,000 robot poles inside of the bound. In this figure, the blue points are sampled in the hypercube bound, and the vertical x represents the position of the n effector. The orange line indicates the boundary constraint for the n effector. In summary, these results verify that GTE can find tight estimates of the joint tolerance bound. Finally, we reach our conclusion. In conclusion, we propose GTE algorithm to estimate the joint tolerance, and we novelly formulate the local positiveness constraints into nonlinear programming problem. And the proposed methods can find the joint tolerance estimation in real time with great optimality. In terms of the future work, we have successfully solved the local positiveness constraint problem in the context of the robot arm, where the constraint is the form of forward kinematics. And in the future, we would like to explore this method with more complex and non-differentiable constraints, such as the CPF tensor size problem. Thanks for listening, and I'm looking forward to your questions.